So, welcome to the deep dive. We are getting right into it today.
Oh, absolutely. I am ready.
Okay, so I want you to picture something for a second. If every single electric vehicle that is currently registered in California were to plug into a fast charger at exactly 5 p.m. today.
Right. The classic commuter rush hour.
Exactly. The resulting power draw wouldn't just, momentarily strain the local grid. It would require the equivalent of roughly 30 nuclear power plants instantly spinning up to maximum capacity.
Just to handle that single synchronized spike.
Yeah.
It's wild to even think about.
It's totally staggering, and that is exactly what this custom-tailored deep dive is all about. We are exploring the hidden, high-voltage world of electric vehicle infrastructure.
Because the mission today is to uncover the massive, behind-the-scenes technological leaps happening to ensure this EV revolution doesn't completely melt our power grids.
Right, and we have a great stack of sources for you today. We are pulling from evaluations by the U.S. General Services Administration, some really fascinating research out of the National Renewable Energy Laboratory, or NREL.
Plus, we're looking at market developments in India, China, and Europe.
So, you probably see EVs everywhere now, right? But have you ever stopped to think about the sheer amount of electricity required when they all plug in at once?
That's the thing. Looking at the data, it becomes immediately apparent that the bottleneck is no longer the vehicle technology itself. We are dealing with a massive infrastructure stress test.
Because our grid architecture was designed for, the continuous, predictable loads of the 20th century.
Exactly. Not the volatile, highly localized mega spikes of modern high-speed charging.
But before we can even talk about the power grid, we really have to look at the immediate consumer experience, like actually finding a plug.
Oh yeah, the app chaos.
Right. For years, the charging landscape has been severely fragmented. Drivers have to juggle, half a dozen different proprietary apps, distinct payment gateways, siloed network maps.
It causes major range anxiety for consumers.
Okay, let's unpack this for a second. Imagine if every gas station brand required a totally different proprietary nozzle and a separate smartphone app just to pump gas. That's the friction we are finally fixing.
And we are seeing the leading edge of that fix happening in India right now. There is this new partnership between Bolt.Earth,
which operates a peer-to-peer network with over 100,000 chargers, right?
Yep. They partnered with ChargeZone, which is a massive public fast charging operator, and they've implemented deep API interoperability.
So what does that actually mean for the driver?
It means a driver can access over 1,500 fast charging locations for four-wheelers on a single app.
Yeah.
They don't need to toggle between different networks or register a new RFID card.
The backend just seamlessly handles the token exchange and the payment.
Exactly. But, and this is crucial, while software interoperability totally solves the driver's headache, it highlights a much bigger physical problem.
Because now you have hundreds of drivers seamlessly routed to the same local commercial district at 5:30 p.m.
Right. What happens to the neighborhood transformers when thousands of fast chargers are used simultaneously?
Yeah, those legacy distribution grids were never modeled for 50 to 150 kilowatt power spikes appearing out of nowhere.
If a developer wants to drop a new fast charging station into an older retail parking lot, the local utility usually has to completely tear up the street.
Just to lay thicker copper and upgrade the substation transformers.
Which takes years of municipal permitting. The capital expenditure is paralyzing deployment.
Which brings us to the workaround. The U.S. General Services Administration and the Joint Office of Energy and Transportation have been evaluating these things called battery-buffered DC ultra-rapid chargers.
A very long name for a very elegant solution.
I have an analogy for this. So what does this all mean? It sounds exactly like how a toilet tank works.
Okay, I like where this is going.
Right, like it fills up slowly from a small pipe, but gives a massive, powerful whoosh of water right when you need it.
Yes. That is actually a perfect analogy. The system draws energy continuously at a moderate rate from the grid, say 50 kilowatts, into a battery storage unit.
The tank.
The tank, exactly. And then it discharges it rapidly into the EV when it plugs in. The Joint Office stats show that if appropriately sized, these can reduce grid service capacity needs by 50 to 80%.
That's massive. You completely bypass the utility trenching.
And the GSA evaluations show potential for 60% energy savings, faster recharge rates. We're talking up to 320 kilowatts for a single vehicle.
And the physical footprint is surprisingly tiny, right?
Very tiny. It's basically a 10 by 10 foot box feeding 2 small dispensing stations.
And beyond avoiding grid upgrades, it really helps businesses reduce operating costs, specifically demand charges.
Right, because commercial electricity rates penalize severe spikes. If you smooth that draw into a flat, continuous line using the battery buffer, you dodge those massive penalties.
Plus, you get increased resiliency. If the grid fails, the station can still operate using its stored power. The GSA projects a payback period of just 3 to 4 years.
What's fascinating here is the risk factor. If your localized battery depletes, the entire system grinds to a halt. You drop from a 300 kilowatt ultra-fast charge to a 50 kilowatt trickle.
Which ruins the whole consumer experience.
Exactly. So planners have to rigorously size these batteries. They use 2 metrics. The first hour calculation to handle a sudden synchronized surge of vehicles.
Like 4 utility trucks pulling up at once.
Yep. And the design day forecast. That's the heaviest projected charging demand. Planners typically model for the 99th percentile day projected for the year 2030.
Wow, planning that far ahead.
They have to.
Yeah.
But this brings up another massive hurdle.
Wait, let me guess. Aren't we just moving the problem? I mean, if we need massive batteries sitting next to every charger, where are all these batteries going to come from? If we use EV batteries to charge EVs, aren't we just putting more strain on the exact same critical materials supply chain?
This raises an important question, and it's exactly what NREL has been focusing on with their behind-the-meter storage, or BTMS research.
Behind-the-meter storage?
Right. They are targeting the 1 to 10 megawatt-hour range, and they are explicitly designing these stationary batteries without critical materials.
Oh, because they don't have to move.
Exactly. In an electric vehicle, mass and volume are the ultimate enemies. You need lightweight, highly energy-dense materials like lithium and cobalt.
But a battery bank sitting stationary behind a retail center has no weight limits. It can weigh 30 tons. It doesn't matter.
Precisely. You can rely on heavier, highly abundant, vastly cheaper elements. And this completely shifts the economics.
What are the targets NREL is aiming for?
They are targeting an installed cost of $100 per kilowatt hour and a 20-year lifespan.
20 years? That's what, like 8,000 cycles?
It's about 8,000 cycles, yeah.
Right.
And hitting that $100 target unlocks roughly a 40% lifetime savings for operators.
That is huge.
It really is. And here's why they can hit it. In an EV, the actual battery cells are the most expensive part. But in these stationary BTMS arrays, the balance of plant costs.
Meaning everything besides the cells, like the cooling and the casing?
Right. The balance of plant is roughly 60% of the total cost, compared to just 30% in an EV. So system optimization rather than exotic chemistry is the real key to cheap deployment.
So we've basically solved the local grid problem for passenger cars. But what about the big stuff? Transportation accounts for 10% of carbon emissions, and heavy-duty trucks make up 40% of that.
It's a massive chunk.
How do you electrify a 40-ton beast on a tight delivery schedule?
China's actually leading the aggressive push here. They have a target of 40% penetration for new energy heavy-duty trucks by 2030. That's about 1.6 million units.
And the economics are just undeniable now. The total cost of ownership, or TCO, for an electric heavy truck is roughly $91,000 a year.
Compared to about $117,000 for traditional fuel.
But you run into a huge physical problem with heavy-duty trucks. The weight paradox.
Right. Roadway regulations strictly limit the maximum vehicle weight. If you install an insanely heavy battery to get a 600-mile range, you lose legal cargo capacity.
Every pound of battery is a pound of paying freight you can't carry, so you use a smaller battery.
Which means you have to recharge constantly.
And in logistics, sitting idle for 3 hours at a charger destroys your profit margin.
So the industry is leaning into 2 main solutions. The first is automated battery swapping.
CATL is aiming for 900 swapping stations by 2026, right?
Yes, a robotic arm just swaps the multi-ton battery in minutes. But standardizing battery sizes across every global truck manufacturer is, well, practically impossible.
Right, so for everyone else, you just have to shove an astronomical amount of energy into the vehicle really, really fast.
Enter the Megawatt Charging System, or MCS. It's rolling out in Europe and the US in 2026.
Okay, here's where it gets really interesting. I was looking at the specs for this. Up to 3.75 megawatts, 3,000 amps, and 1,250 volts DC. It's 10 times faster than a standard fast charger.
It's unbelievable power.
Oh, wait, 3.75 megawatts. Wouldn't a cable carrying 3,000 amps of continuous current be, like, thicker than my leg or just instantly melt?
Oh, it would completely melt standard copper. The engineering marvel behind this is the IEC TS 63379 standard.
That sounds complicated.
It's basically a masterclass in thermal management. You absolutely have to use liquid-cooled cables.
So they pump fluid through the charging cable.
Yes, dielectric fluid flows continuously right over the copper conductors and into the connector pins themselves. Plus, there are incredibly strict software interlocks to handle that much power safely.
Because if there's even a microsecond of lag in the cooling, you get a catastrophic failure.
Exactly. And the scale of deployment is ramping up. The Milans project is building 284 of these stations across 10 EU states. And Tesla is installing 1.2 megawatt stations in California and Nevada for their Semi.
And the timing of this charge perfectly solves the logistics dwell time problem. It pushes a 20 to 80% charge in 30 to 40 minutes.
Which perfectly aligns with the EU's mandated 4.5-hour driving break for truckers.
That is so smart. The charge time literally just hides inside the legally mandated downtime.
Exactly. It ceases to be a hurdle and just becomes part of the workflow.
Okay, so we've seen how the infrastructure is adapting for commuter trucks. Now let's look at how this impacts massive commercial fleets and ultimately your own driveway.
The fleet application is really interesting right now. Look at Uber's upcoming mid-2027 robo-taxi launch in Houston.
Right, they are using Lucid and Euro vehicles. And to make this work, they've leased a 50,000 square foot depot with 40 fast chargers and 15 maintenance bays.
Highlighting what we call a charging as a service or CaaS model. A third party manages the heavy electrical infrastructure, and Uber just pays for guaranteed uptime.
But bringing it home to the individual listener, the real magic is vehicle-to-grid, or V2G tech.
This completely flips a century of utility architecture on its head.
Think about this for a second. Your car isn't just transportation anymore. It's becoming a mobile power plant sitting in your garage.
Yes. The landmark partnership between PG and E and Tesla is a perfect example. They are using the Cybertruck and its PowerShare tech.
And the financial incentives are wild. Up to $4,500 for customers to install the gear and participate in the emergency load reduction program.
You literally get paid to sell power back to the grid during peak events, like a massive August heat wave.
But V2G isn't a new concept. Why is it suddenly commercially viable now?
If we connect this to the bigger picture, the specific breakthrough here is that this is an AC-based bidirectional flow.
Alternating current.
Right. Historically, to do V2G, a homeowner had to install highly expensive, specialized DC equipment on their garage wall to convert the power.
Which costs thousands of dollars.
Exactly. The new architecture removes that need entirely. The conversion is handled by the advanced power electronics inside the vehicle itself.
It drastically lowers the barrier to entry.
And it turns hundreds of thousands of civilian vehicles into a massive, decentralized grid buffer.
Wow. Okay, we've covered so much ground today. Let's recap. We started with the messy, fragmented apps in India and how unifying them creates local spikes.
Which we fix with battery buffer chargers, those electrical water tanks.
Right. Then we scaled up to those mind-blowing 3.75 megawatt liquid-cooled truck chargers.
And finally brought it all the way down to turning your driveway into a mini power plant.
It really is a complete reimagining of the energy landscape.
But, all of this integration leaves us with one really lingering question to ponder.
Oh, what's that?
Well, if millions of our cars become the actual backbone of the electrical grid, literally supplying power to our homes and cities during extreme weather or grid emergencies, who really holds the power switch?
Oh, wow.
Right. Is it you, the homeowner? Is it the utility company desperately trying to balance the load? Or is the car manufacturer's proprietary software algorithm silently making the call?
That is a wildly complex dynamic to think about. Who actually has the override?
Exactly.
Well, that is definitely something to chew on the next time you plug in. Thank you for joining us on this deep dive. We hope you enjoyed the journey into the high-voltage hidden world around us. Keep questioning the systems you use every day, and keep learning.